All right, let's go right into it. So you'll see on screen, this is a famous picture up here. That's a picture of the Hubble Space Telescope. And that space telescope launched back in 1990 when I was in middle school. Now you've got something brand new up there. On Christmas Day last year, the James Webb Space Telescope launched. NASA's Hubble Space Telescope is 32 years old and it's still working. But we have a new one, the James Webb Space Telescope, and I'm going to tell you folks today a little bit about the science of space telescopes. You might wonder, why do we need a space telescope? After all, we can see space, right? Space looks really good here from Earth. You can see it at night, especially if you go far away from the city lights to any place that's dark. What can you see? You can see thousands of stars. And if you have a telescope or binoculars or a fancy observatory, like the kind we build with giant telescopes inside, you can see out all the way to the edge of the universe. But there's a problem. Have you ever swum down under the surface of the water and looked up at the surface of the water? It's all blurry, right? Because the water is blurry. And for an astronomer, being stuck on Earth's surface is a little bit like being at the bottom of a swimming pool and looking up at space. Because as great as space looks, we always have this to contend with. You don't always have clouds, but you always have Earth's atmosphere. And one of the things we think of is, oh yeah, well, we can see through Earth's atmosphere, but not completely. Earth's atmosphere absorbs light. That's why the sky looks blue. That's why at sunset, the sun looks red. And it turns out, even beyond the light we can see visible light, but there's also shorter wavelength light, like ultraviolet, X-ray, and gamma ray light. And there's longer wavelength light, like infrared, microwave, and radio light. The problem is Earth's atmosphere blocks some of that light almost everywhere. Even in visible light, where you see the rainbow in this image, Earth's atmosphere blocks some of that light. But if you want to see where Earth blocks all of that light, you have to go to space. You're limited with what you can do from the ground. And we've built amazing, amazing telescopes and observatories here on the ground. We have some of the largest ones we've ever built here on the surface of Earth, on the top of some of the greatest mountains we have, like on the top of Mauna Kea in Hawaii, in the Canary Islands in Spain, and on the Chilean plateau of the Andes Mountains in Chile in South America. These are the best locations in the world for building telescopes, but there's still nothing like going to space. Because from space, you can see almost everything without any of the atmosphere being in the way. You can look at individual galaxies that are close by, and this is a real image of a nearby galaxy from the Hubble Space Telescope. Isn't that amazing? This is what you see in visible light. The nucleus of the galaxy, the dusty spiral arms, those pink spots you see are real. That pink comes from when you have hydrogen atoms in space, that new stars ionize them. And you might know that matter is made up of atoms and molecules. Hydrogen atom is the simplest one with one proton and one electron. When you make new stars, it's so energetic, it kicks the electrons off of the protons. And then when the electrons fall down, they cascade down the energy levels. And one of them, you might learn in science class, when you drop from the third energy level down to the second energy level, it makes a red glowing light. And that pink you see, that red spot in these images, that's where that is exactly happening. We have other galaxies that do weird things, like collide together. And they can make weirdly shaped galaxies. This one on the right is known as the Cartwheel Galaxy. And that's something that the Hubble Space Telescope has seen. But one of the things I love most, remember, I showed you we only see visible light, but there are all these other wavelengths of light. And when you look invisible light versus, say, infrared light, check this out. This is the same region of space. On the left is what it looks like in visible light. And some people are like, oh, look, it's a hole in the universe. It's not a hole in the universe. It's a dust cloud. It's a cloud of dust in between the stars in space. And when you look in infrared light, like you see on the right, you can see all the stars behind it, because infrared light is longer in wavelength and it passes through the dust. That's one remarkable thing you can do from space. Another one is, this was remarkable. This is something they only did with the start of the Hubble Space Telescope. The director of it said, I want to do something ambitious. I want to look at, ready for this? Nothing. This right here is a tiny little patch of sky with nothing in it. No, just a couple of nearby stars, no galaxies, no galaxy clusters. We didn't know of anything there. What they did, this was really risky. Back in 1994, they took a look at that one patch of sky for 9 days. It's just like taking a camera shutter, if you remember an old camera, and leaving the shutter open for 9 straight days, and they wanted to see what's out there. People were worried, like, what if you see nothing? You're wasting all this time of the world's most powerful, most expensive telescope. Guess what? They looked at that region of sky. What came back 9 days later? This. There were thousands of galaxies. They were just too faint and too far away to see. So the longer they waited, the more they left the shutter open, the more they saw, the more universe was out there. In fact, they were able to say, you know what? We can look at these galaxies and we can look at the light coming from it, and we can figure out how far away they are. And it turned out most of the galaxies we were seeing were really far away. The farther away you look, the more stuff there is. In fact, Hubble went and did this for longer. They took bigger regions of space and more time. The greatest view ever is called the Hubble Extreme Deep Field, or the XDF. They spent 23 days observing it. This region of sky is so small, it would take 32 million of those little squares to cover the entire sky. And in that little region of space, they found more than 5,000 galaxies. And still, with all of that, if you said, well, I'm going to take those 5,500 galaxies we found, and I'm going to extrapolate that and say, well, if this is the same in all 32 million of those little patches that would cover the sky, how many galaxies would the Hubble Space Telescope be able to find? And the answer is 170 billion galaxies. And it turns out, with the first deep field image that the new James Webb Space Telescope took, we know there are even more out there. James Webb is seeing things that Hubble could never have seen. So how do you do this? How do you build a space telescope? Why is the James Webb Space Telescope so good? And it only started science operations this summer. It's been operating only for about 5 months in science mode. What has it seen so far? Let's take you through this. The first thing you need if you want to gather light as a telescope is you need a mirror. And James Webb Space Telescope didn't use a normal optical mirror. It used a gold-coated mirror. Why? Because gold is super, super effective at reflecting not visible light, but infrared light, longer wavelength light. Remember that light that gets so efficiently absorbed by Earth's atmosphere. Then once you gather that light, you need to focus it into instruments. So we build these instruments that are ultra sensitive to certain types of light, that can analyze it and collect it and synthesize it together. Some instruments, you can say, I'm going to make my instruments cold enough, but other instruments, you have to actively cool them, right? Infrared light is the same as heat. If you go and you see something that's glowing red hot, you know it can burn you. But if you see something that isn't glowing red hot, like a pot on the stove, it can still burn you because it gives off infrared light. It gives off heat. So what we do is we build cryogenic coolers. This is the cooler on the coldest instrument on the James Webb Space Telescope, the mid-infrared instrument. In order to take that mid-infrared data, James Webb Space Telescope needs to keep that instrument at 6 Kelvin. That's 6 degrees above absolute zero. So this instrument has a special cooler that uses liquid helium to keep it cold. Then you take all of those segments and you stitch them together. And that's what James Webb Space Telescope's primary mirror looked like. And that is the actual scale. Then you need to install all of the instruments together on this module you see in the back. This is one of the instrument teams there. And then you load this telescope, you fold it up, you load it onto a rocket, and you launch it into space. I got up early. This happened Christmas morning of last year, December 25th last year. They launched this into space. And I was so excited because what happened was they launched it so good. The launch was so pristine. This thing had to go 1.5 million kilometers away from Earth, and it needed to deploy and it needed to calibrate itself. And it was such a good launch that we think this telescope is going to be operating for more than 20 years before it runs out of fuel. I'm going to show you, you're going to be so unimpressed. I'm going to show you the very first image that the James Webb Space Telescope took. Get ready to be unimpressed. Are you ready? Here it is. Wow. How unimpressive is this? Do you know what's remarkable about this image? This image is just of one star. Each of these individual mirror segments on James Webb Space Telescope, there are 18 of them, corresponds to one of these points of light. So the first thing they did after they took this image was they said, I want to identify which segments are creating which image. And they did. And then they said, okay, now we're going to calibrate this so that each of these 18 images of the same star shows up in the right place. So they went and calibrated the telescope from 1.5 million kilometers away, and all of a sudden it started looking like this. And you'll say, hey, this looks a lot more like this pattern. Can we take these 18 images and focus them together to make one single image of a star? And the answer was yes, that's exactly what they did. That's the first star the James Webb Space Telescope saw. And you look at this and you say, well, hang on, why is this star so spiky? I like my stars to just be single points of light. Why is this one full of spikes? And the answer is because of the shape of the James Webb Space Telescope mirror. If it was a perfect circle with nothing in the way, you would see just a single star like this. But James Webb is hexagonal shaped, and it's made out of 18 hexagonal segments, and those segments have gaps between them, and it has wires in front of it to hold the secondary instruments in place, just like this. It has that secondary mirror that reflects light onto the instruments. So that's why the star looks like this, because it has all of these confounding factors. What does that mean? Well, instead of this, when we took the full data in all the different colors and stitched them together, this is what the James Webb Space Telescope saw. And sure, this is a bright nearby star, but look behind it. Look at all those smudges. Look at all those points of light. Every individual one of those is its own distant galaxy. We see that there are galaxies everywhere we look. So then we said, we've got this telescope calibrated. We can start taking data and seeing the universe like we've never seen it before. So you'll remember I showed you this galaxy from the Hubble Space Telescope. James Webb Space Telescope has 2 imaging cameras. One is the near infrared camera, which looks at light that's just a little bit redder than our eyes can see. And when it looked at this galaxy, here's what it saw. This traced out the dust, the new stars, the heated heavy elements that are in there. But you can say, you know what? We can go even longer with that cooler it has on board with this mid-infrared instrument. The James Webb Space Telescope can go from looking at that light that's just a little bit longer in wavelength than what our eyes can see to something that's much longer in wavelength. And when we do that, instead of this, here's what we see. And this shows different features. This shows material that's colder. This shows material that's gravitationally contracting, that's going to form new stars. And you'll notice that weird blue stuff at the center of the galaxy. That is a region where you start to see into the individual stars and black holes at the galactic center. Every system looks different. This was the Cartwheel Galaxy as seen by Hubble. This is what it looks like seen with the James Webb Space Telescope. And here's what it looks like in both near and mid-infrared light together. That spiky thing, those spiky things you see over here and down at the bottom, those are stars within the Milky Way. You have to see past them to see what's beyond. So those stars with those spikes, they're in the way. We have a saying in astronomy that one astronomer's noise is another astronomer's data. So if you study stars, you're going to be mad at those galaxies in the image. And if you study galaxies, you're going to be mad at the stars of the image. But that's okay. It means there's something for everyone. I'm going to show you the same region of space that Hubble saw, that James Webb's near-infrared camera saw, and that James Webb's mid-infrared camera saw. Take a look at this. This region of space is called the cosmic cliffs. On the north side, on the top side, that's where stars have blown star-forming material away. But down below it is where stars are still forming new material. Take a look right here, right? You can see this little serpent head, and then this little serpent head. This is Hubble. Take a look right here at this newborn star being formed. With visible light data, it only kind of pokes out through this dust. In near infrared data, it shines brightly, but it's still obscured. But in mid-infrared data, it shines like there's nothing in the way at all. I think this is amazing. You might wonder, can you use this space telescope to look at planets in our solar system? Oh yeah, here is the James Webb Space Telescope's very first image of Jupiter. What do you think? Well, the great red spot doesn't look red, but you can see things that you can normally not see even with really good telescopes. Look at this. Do you know what this is? This is one of Jupiter's rings. Jupiter, just like Saturn, has rings. You can't see them in visible light from so far away, but the James Webb Space Telescope can see them. What are these blue things at the poles? Do you know what? Just like Earth has the northern and southern lights, we have aurora at the poles. Jupiter has them too. This is one of Jupiter's moons. And way back here, these are background galaxies. We can even see distant galaxies in the direction of Jupiter. You might say, well, what else can you see? What if you looked at a galaxy that was active, that was forming stars all throughout it? What would it look like? And the answer is, through James Webb's eyes, it looks like it's on fire. That bright spot at the center is actually a supermassive black hole that is so brilliant that it shines in infrared light. You can look at a star-forming region, even, like I'll show you here, in another galaxy. And you can see all these dusty clouds, all this matter that can gravitationally collapse and form stars. But look over here towards the center. Do you see that cluster of new stars? James Webb can zoom in on that. Look at this. Inside here, These are the most massive stars we know of. At the center of the brightest spot is a star that is 260 times as massive as the sun. It's the single brightest, most massive star we know of. It shines over 8 million times as bright as our sun. Because James Webb sees all these different wavelengths of light that our eyes can't see, it can look at star formation in here and say, hey, look, I have atomic hydrogen, I have molecular hydrogen, I have hydrocarbon dust. It can tell you what atoms and molecules and ions are present in space. You might wonder, okay, if I look at individual stars like this, could I ever see if it has planets around it? And the answer is yes, because the James Webb Space Telescope has something called a coronagraph on it, where it blocks the light from a star, and if there are planets around it, it can see those planets directly. Here is a real image of a star that we know of. It has a name, and it also has a giant planet around it, a Jupiter-sized planet around it. So we point the coronagraph at the star. This star is the location of where the coronagraph is blocking it. And you can see with both the near infrared camera on the two images on the left and the mid infrared imager on the right, you can see the planet even in the glare of the star. Every once in a while, you'll find a star where a planet passes in front of it and blocks some of the light. Well, guess what? That starlight is going to pass through the atmosphere. You're going to get a ring of atmosphere that starlight passes through, and you can find out what is a distant planet in another solar system. What is its atmosphere made out of? So we say, oh, look, from the light that it absorbs, we can tell there's carbon dioxide in there in the atmosphere. In fact, you can see that in terms of how much light gets blocked. This tells you, look, this is a giant exoplanet named WASP 39b, and it has carbon dioxide. We hope someday to use this for Earth-sized planets to see, is there a planet with nitrogen and oxygen in its atmosphere, with carbon dioxide and methane, with water vapor in its atmosphere? If we find that, that might be the first way we find a planet outside of our solar system with life on it. You can use the James Webb Space Telescope to point at lots of different regions of space next to each other and stitch together this giant region of space and find some of the most distant galaxies you've ever seen. Some of these galaxies are so far away. Remember, light can only move at a finite speed, the speed of light. So when we look far away in space, we're seeing things as they were a long time ago when light was being emitted. Some of these galaxies are more than 13 billion years old. And as we look, if we arrange them on the left to say this is closer galaxies, and on the right, these are farther away galaxies, you can see that the closer ones are larger and more evolved and redder in color, whereas the farther away ones are bluer and smaller and less evolved. Galaxies change over time. You can even use the James Webb Space Telescope to point at stars that are still forming, that have protoplanetary disks around them. And when you see that, you see solar systems being born. You see gaps in the dust around these newborn stars where planets are forming. This is just a sample of 20, but as we go into the future, James Webb is going to get hundreds of these. But I think the coolest image I've ever seen, I'm going to show you something. This is called the Pillars of Creation. 7,000 light years away in our own galaxy, there's a nebula called the Eagle Nebula, and it's actively forming new stars. So this on the left is what Hubble sees in visible light, and then on the right is what it sees in near infrared light. But the James Webb Space Telescope can do better. When the James Webb Space Telescope looks in infrared light, Here's what it sees. This, I think, is amazing. You can see so much detail. You can see the stars behind and inside it. But my favorite ghostly view is what you see when you look in mid-infrared eyes, and not at the stars, but rather at the cold gas that's contracting to form new stars. And this is what that looks like. It's amazing to me that you can see so many different details just by looking in different wavelengths of light. And this, I want to impress on you, is so amazing to me because the James Webb Space Telescope has only been doing science operations for 5 months. And it's going to be up there taking data for more than 20 years. So this, I think, is so exciting because we're just getting started. And what I've shown you are some of the highlights, but it's also the amazing power of what we can see out there in the universe by going to space. So I'm going to stop presenting now because I want to make sure that everyone has chances to ask questions and get your questions answered. But I hope you enjoyed this tour of the universe and understand a little bit of what's so amazing about looking at the universe from space.
Wow. Well,
yeah, I see the applause. I don't need to hear it. I see it. It's way to go.
Yes, come on. Let's give Dr. Siegel a hand. You know, I think that is really incredible. And when you showed us galaxies that was 13 billion years old, but it's like we're seeing it in the present. And something I just never realized was that the further away it is, we're actually looking back in the past, huh?
Yeah, the universe is kind of like this ultimate time machine. If I look at something like the moon, I'm seeing the moon as it was a second and a quarter ago. If I look at the sun, I'm seeing the sun as it was 8.5 minutes ago. If I look at Pluto, I'm seeing Pluto as it was 4 hours ago. But even the nearest star beyond the sun, I'm seeing it as it was years ago. Even the nearest big galaxy, like Andromeda, I'm seeing it as it was millions of years ago. And with the James Webb Space Telescope and Hubble, they're so powerful, we can see galaxies as they were more than 10 billion years ago. And that's amazing because it's only been 13.8 billion years since the Big Bang happened. So we're seeing the universe, the earliest galaxy that we've seen comes from when the universe was just 3% of its current age. And I hope that by next year at this time, we've broken that record and we see back even further.
That's fascinating. So students, think about some questions to ask Dr. Siegel. And the first class that is ready, go ahead with your question.
All right,
Do we have any class that's ready?
All right, Ms. Wisniewski's class. I hope I said that right.
No. It's Rosinski.
Rosinski, awesome.
We thought that last picture kind of looked like a Thanos glove. It was kind of cool. And we want to know your opinion on the multiverse. Do you think?
Oh boy, that's a fun one. So there are two ways. So there's the Marvel Comics multiverse, right? And that's not real. But there are two ways you can have a multiverse in real physical reality. The first one is from quantum mechanics, right? Quantum mechanics is this weird thing that says, I'm used to things having well-defined things, like it's here, it's moving this fast, it has this much energy. In the quantum universe, that's not true. Everything is uncertain. So there's only a probability set of outcomes you can have. Normally we say, okay, I'm going to make a measurement and that's going to determine what it is. But there's an alternative theory of quantum mechanics that says, you know what? All of those possibilities that could happen where a particle could be here or here or here, anywhere, they all happen somewhere. We just get one answer in our universe, but there's a whole multiverse out there, a whole set of universes out there where all of these possibilities happen. Now, this is an interpretation of quantum mechanics. It's not something we can go out and measure and say what happened here, but it is fascinating to think about. Another thing to realize is that our universe that we can observe is only a fraction of what's out there. We can only see back in time a certain distance because we had the Big Bang a finite amount of time ago. Even though the universe expands, light only moves at a finite speed. So there's a limit. There's like a bubble that we can see. What lies outside of that? We think more universe with more stars, more galaxies. And if you think the universe is truly infinite, we don't know. We just know it's at least bigger than a certain size. But if it's truly infinite, there could be enough atoms in enough combinations that somewhere out there are identical copies of all of us having this very conversation right now. And that's another example of how the multiverse could be real. This is a good question. Thanks for asking it.
Hi, this is Miss Parkerson's class.
Woo! Hi, Miss Parkerson.
Hi.
Hello.
We want to know how you got started down this career path. Tell us about your education.
Oh, wow. You want the real story or you want the fake story?
We want the real
story.
Drama.
I will tell you, the real story is after I graduated college, I became a high school physics teacher. And while I was doing it, I realized that wasn't what I wanted to do for the rest of my life. And so I asked myself, what is it that I want to do? We have this word in our society that we treat like a 4-letter word. That word is crisis. We treat people like you should never have a crisis. You should always know what you're doing and you should never fall into crisis. Guess what? Crisis is a good thing. Crisis means the path I'm going down is not the one I want to keep going down. I want to figure something out new for me. And there is nothing wrong with doing that. Most of us are going to do that numerous times during our life. So while I had a job that wasn't 100% what I wanted to be doing, it made me ask myself, what do I want to be doing? And I said, if there was one thing that I could learn in this life and know for my whole life going forward, it would be about where all of this came from. What is the universe? What is it like? How did it get to be this way? How was it created? How did it come into an existence? And what is its ultimate fate? And I learned this is not something that we ask poets or philosophers or theologians. This is a science question. And I can go to graduate school in a branch of astrophysics called cosmology, and I can learn about it, and I can study it, and I can become an expert in it. And that was how I got started doing it, because that was when I decided this is what I want to do. And all you had to do, in my mind, was learn how to work hard enough to become good at it, and you can be anything. And that was what I did. I went to graduate school, and then I taught college, and then I became a researcher, and then I taught college again. And while I was doing that, I was like, let me start communicating science. Some things you learn and you get good at because you're naturally gifted and talented at it. And other things you have to work hard at and you have to practice. But you do both of them. You take where your interests are, what you're good at, what you're talented at, and you practice it. And you can go as far as you want in life. That's what I'd recommend to anyone. That's what I did. And you are going to have multiple crises over your life. Don't shy away from them. Have them and pick the path that's right for you. That's what I did, and I've never looked back.
Hello.
Yeah, you got the real answer, Miss Parkinson's class.
This is Miss Wilder's class, and I have a question that's regarding...
Go for it, Miss Wilder's class.
I have a question regarding the formation of solar systems and the planets. You said that they're forming planets, right? Do you think it's ever possible to have species like us in those planets and for us to ever integrate with them or anything?
This is a great question. I love this question because this is the big one, right? One of the things we wondered about ever since we first look up is, are we alone? Are we alone in the universe? Or is there life out there? And more than life, is there complex, intelligent life? Is there someone to talk to, someone to communicate with? Yes, it's absolutely possible. We know what the laws of physics are, what the laws of chemistry are, and how biology works, at least on planet Earth. We've never found another planet that has biological activity on it, at least that we've discovered, but we found all the ingredients for life. We find them not only on planet Earth, we find them all throughout space. We've had meteorites fall to Earth and we look inside them, and guess what? We use about 20 amino acids in mammals to take care of all of our life processes. In this meteorites, we found like over 80 different types of amino acids. We found all these different organic complex molecules in interstellar space, in outflows around young stars, and yes, even in the protoplanetary disks that are forming planets themselves. People use a radio telescope array located on the Chilean plateau of the Andes called ALMA, the Atacama Large Millimeter Submillimeter Array. And they have found these complex organic molecules in dozens of these protoplanetary disks. Now, we haven't found life yet, but one thing I'll remind you of is here on planet Earth, we know we were just one lottery ticket, right? Planet Earth was one lottery ticket and we won. We won the lottery. But here are two questions that we don't know the answer to. Number one, what are the odds of winning any prize? We won a prize here on Earth, but what about the planets where life comes into existence and then goes extinct before getting complex? And what about all those planets where you can have a diversity of creatures, plants, animals, fungi, or something completely different, but they never become intelligent or technologically advanced? Or, and this is my favorite possibility to think about, what if we're not even the grand prize? What if there's some planet out there where life is way more complex and way more advanced and way more intelligent than we can even dream of? So I'll say we believe in all of this universe with the sextillions of stars within it, with planets around more than half of the solar systems we know of. There's almost certainly life out there. But if we want to know how abundant is it, if we want to know what are the diversities of life and what are the chances of getting like a human-like intelligence or better, we have to look. So I'm hopeful that in the next 10 or 20 years, we'll find life beyond Earth for the first time. Whether it's human or not, or intelligent or not, or we can communicate with it or not, that's something we're going to have to wait to find out. Maybe one of you will be the ones who do it.
Thank you for answering our question, by the way.
You're welcome. Who's next? Are we ready for Miss Musso's class? I can't hear you, Miss Musso's class.
Does any other class have a question? Yes, come stand up. We have a question here. Which class are you in, buddy? Miss Perez's class? Okay. Come over here. And hopefully you can see him. Stand right there. Go ahead and ask the question.
How could
Loudly.
how could there be an infinite? How could the universe be infinite?
So the question is, how could the universe be infinite, right? And this is a big question, right? Because we don't know if it is infinite or if it is finite. The problem with a science like physics or astronomy is you only know what you can measure. What lies beyond that? We can't be sure. We have to keep our minds open. So I can say the universe is at least as big as far as I can see. But what lies beyond what I can see? There could be more universe. There could be a lot more universe. And if I say how much more universe could there be, there's no upper limit. There's no bound that observational data comes to me that tells me, oh, it can't be any bigger than that. So you have to keep your possibilities open, even if you feel like, nah, this is too mind-blowing, it's too wild, it couldn't possibly be that way. Sometimes even our craziest, wildest imaginations and where they take us, it's not wild enough. So I would say if you have an idea and you're like, oh, but that's too wild, it can't be right, maybe it needs to be exactly that wild to be right. So don't rule it out unless the data tells you you can rule it out. Everything else, keep it in your mind, because it's possible until you rule it out.
Thank you very much. Does anybody else have any questions?
By the way, Ms. Muso's or anyone else's class, if your microphone isn't working, we have a chat window. So you can type in the chat window what your question is, and I will see it and read it out loud.
Okay. All right. Wait, Muso's typing.
Hi, do I hear Ms. Boris's class? Did I say that wrong too?
Hi, this is us. Okay, we have two questions actually. Okay, first of all, do you have a middle school memory that has stuck with you of a favorite teacher or a favorite thing that they taught you?
Oh boy. So middle school was not a positive time in my life. So if you're asking, did I have a favorite middle school teacher? The answer is no. No, I would like to forget almost everything I experienced in middle school. And I'm sorry if that's a bummer for some of you to hear. But no, I don't really have a favorite middle school memory. I guess if I had to pick one, my favorite middle school memory was when I started 9th grade and got to leave it behind me.
So
What's your second question?
This is a good example because you're saying, you know, you can have a miserable life at school and still succeed in life. You don't have to have it ruin your life. You can succeed. All right. Our second question is, what is the oscillating something?
No, what is your opinion on an oscillating universe?
What is your opinion on the oscillating universe?
So the oscillating universe was an interesting alternative to the Big Bang, right? Because it said instead of having everything be hot, dense, and expanding from there, what if things expand and then they reach a maximum point and then they contract again, and then they contract but not all the way down, and then they expand again? What if it does something like that? And the answer is, well, we can test this, because if we look further and further and further away, remember, we're looking back in time too. So when things were earlier, farther away, we should see that maybe they weren't expanding faster and faster. Maybe at some point it looks like there was a contraction. But it turns out that as far back as we can look, and we can see light from the universe back when it was only a few thousand years old, not a few billion years old, but a few thousand years old, it was expanding in an unbroken streak as far back as we can look. When we look back, we see, you know what? There was a time when there were no galaxies, before any stars or galaxies had formed. And in fact, when you go back farther, you can say, oh, wow, there was a time when things were so hot and dense that you couldn't even make neutral atoms. And so hot and dense that atomic nuclei, the things that make us up, atoms, the nuclei with protons and neutrons, they would have been blasted apart. So since we've gotten the evidence for those things, oscillating doesn't look like what it's doing. In fact, you can think of the Big Bang as a race. Like the Big Bang is a starting gun. And it's a race between the expansion of the universe, which drives everything apart, and gravity, which tries to pull things back together. On little scales, scales like planets and solar systems and individual galaxies, gravity can win. But on the overall scale of the universe, expansion is king. Outside of our local group, which includes the Milky Way, Andromeda, and maybe 120 other little galaxies, every other galaxy is expanding away from us. And as time goes on, they'll only get farther and farther away. So oscillating universe, good idea, bad evidence. Sometimes the best ideas don't pan out.
Thank you.
Yeah.
I think we
I got
time for
a question online from Muso's class. It says, If two black holes collide, then what happens? Also, what color is the inside of a black hole? So the two black holes colliding is wonderful because I would have told you the theory of what happens if you had asked me this question before 2016. But in 2016, we have gravitational wave detectors that have seen black holes inspiraling and merging together. There are two super powerful ones in the world. There are others, but two of them are super powerful. They are LIGO Hanford and LIGO Livingston. LIGO Livingston is in Louisiana. It's right by you guys. You have one of the two best gravitational wave detectors in the world. And what they saw was two black holes. One was the first ones they ever saw merge. One was 36 times as massive as the sun. One was 29 times as massive as the sun. They inspiraled, they emitted gravitational waves, so their orbits decayed, and they merged together. And they produced, this is the crazy part, they produced a black hole that was 62 solar masses. Hold on. 36 plus 29 does not equal 62. It equals 65. What happened to the other three? And the answer is it got converted into energy. Have you ever heard of Einstein's equation E equals mc squared? That tells you how you can convert m, mass, into energy. When those two black holes merged together and they produced gravitational waves, we were able to see those gravitational waves even from hundreds of millions or billions of light years away. Those gravitational waves that were produced were so energetic that for the few hundred milliseconds we detected them over, there was more energy in those gravitational waves than there was from all the shining stars in the observable universe combined. So what happens when two black holes collide? They make a bigger black hole and they emit these ripples that propagate through space-time. Inside a black hole, I got bad news. Everything that goes inside a black hole that crosses over the event horizon is going to get sucked into the central singularity. The only thing that's going to provide color or light is the light that falls in with you, which is good because if you're reading The Count of Monte Cristo as you fall into the black hole and you are on page 1497 and you want to know how it ends, you will be able to finish the book before you hit the singularity. The lights stay on inside your spaceship when you fall inside a black hole, but everything shifts towards bluer and bluer wavelengths, and eventually you get torn apart. And here's Miss Sprague's question. I have a student interested in spaghettification and wanted to know what your favorite kind of pasta is. Well, I just baked a macaroni and cheese for Thanksgiving, but I prefer cavatappi if you can get your hands on that. Those are the spirally elbows. But spaghettification is called that because when you fall into a black hole, think about it. You're this person, you're an extended object, but a black hole is a singularity. You're going to have some part of you that's closer to the black hole and some part of you that's further from the black hole. The part that's closer gets pulled on more strongly. So you get stretched into a long, thin piece of spaghetti. If you were to say, fall into a black hole, feet first, your feet would get pulled in more and your head would get pulled in less and you would get stretched apart. It's a disgusting and very painful way to die, like being drawn and quartered in old medieval times, except not by horses and ropes, by a black hole's gravity.
We have time for one more question, Dr. Siegel. We have
Do it. Who's the last question?
Okay. So, I've heard things about like what happens when the sun disappears. It'll like take 8 minutes for the Earth to notice. What will happen to the orbit of the planets if the sun disappears?
So is this asking what happens to the orbits of the planet when the sun swells, becomes a red giant, and goes through its death throes? Okay,
Yeah.
so let's do this. So stars age, and when they age, they burn through the fuel in their core. The sun right now is fusing hydrogen, the lightest element, into helium, the second lightest element. When this core runs out of hydrogen, that's what makes the radiation that holds the star up against gravitational collapse. So the core is going to start to contract. And when things contract, they heat up, right? The sun is a dense, massive thing. So the heat can't escape. It heats up and boom, it'll start fusing helium into carbon. That emits more energy than fusing hydrogen into helium. So the outer layers of the sun are going to expand and some of them will get blown off. When that expansion happens, here's what's going to happen. Mercury will get swallowed by the expanding sun. Venus will get swallowed by the expanding sun. Earth is going to be close. The sun expands, but as it blows off its outer layers, Earth's orbit is going to spiral outward. We think Earth's orbit is going to spiral outwards by about 10%. But the sun is going to expand to be about 115% of Earth's orbit. So we think Earth's probably going to get swallowed too. Mars should be safe and everything beyond it will be safe. But this is a big question that we don't know the answer to yet. Some simulations say, guess what? Sometimes Earth is safe. Sometimes one of the 4 inner planets is going to get ejected over the next few billion years because they gravitationally pull on each other. And sometimes Earth will just get swallowed. So we don't know what's going to happen, but we do know the sun's going to run out of hydrogen fuel. It'll expand. It'll become a red giant, and then it'll blow off its outer layers and contract down to a white dwarf. Will Earth survive? Will there be a charred corpse of the Earth left? Nobody knows.
That was fantastic. Thank you so much, Dr. Siegel. I think that's all the time we have today. Let's all give him a hand, please.
You guys have been a great middle school. Thanks for joining us. Mr. De Silva, thanks for setting this up. Have a great day. And remember, anything you want to be, work hard towards it, and you can do it. I believe in you, and I want you to believe in yourselves.
Thank you very much. All right, bye.
All right, bye, everybody.